The demonstration that we just did with the Pyrex beakers and the baby oil is based on a concept called refraction. Refraction is the bending of a wave. Specifically in the context of this unit, it would be the bending of light. Now, why does light bend? Why does light bend? Why does it change direction? Well, when light goes from one medium to another, it changes speed. And it bends or changes direction as a result of that change in speed. That change in direction due to the change in speed is called refraction. You guys have all seen this before, right? You put a pencil in water and it looks like the pencil is bent. Clearly it's not. The pencil is actually going into the water straight in just like this. Why does it look to be bent? Well, light reflects off of the pencil up here. It doesn't bend. We see the pencil because it's reflecting off of it, but it doesn't bend when it goes from air to air. So the pencil appears to be where it really is. But when light reflects off of the pencil that's inside the water and then gets to the boundary between the water and the air, it changes direction due to the change in speed when the light went from the water to the air. Because the light changed speed and the light changed direction, it's going to make us think that the pencil is somewhere other than where it really is. That's called refraction, right? The bending of light due to the change in speed of the wave when light goes from one medium to another. Now, let me give you another term here called the index of refraction. In the demonstration that we just did, the index of refraction of Pyrex was the same as the index of refraction for baby oil. Index of refraction is kind of an everyday understanding. It's the amount that light bends when it's going into that medium. But technically, we'll define it as a ratio. The ratio of the speed of light in a vacuum, which of course is just 3 times 10 to the 8 meters per second, the speed of light in a vacuum to the speed of light in the medium. You want to find the index of refraction for air, then we would say it's the ratio of the speed of light in a vacuum to the speed of light in air. You want to find the index of refraction for diamond, which is much, much higher. You would say it's the ratio of the speed of light in a vacuum to the speed of light in a diamond. We're going to write this down as a little equation, an equation that, by the way, does not appear on your data sheet, but really is just a mathematical statement of the definition. N is equal to C, which is a symbol that we use for the speed of light in a vacuum, 3.00 times 10 to the 8. Top number is always going to be the same there. Divided by V, the speed of light in air, diamond, water, glass, whatever the material is. What do you think the units for index of refraction would be? What do you think the units for N would be? Meters per second divided by meters per second, cancel. There are no units. There are never any units for a ratio. Right? Magnification is a ratio of HI to HO. What are the units for magnification? There are none. There's never any units associated with the ratio. Index of refraction, the ratio of the speed of light in a vacuum to the speed of light in the medium. It's really just a measurement of how much light bends. Okay, the index of refraction for diamond is much greater than the index of refraction for glass because the speed changes more. Therefore, light bends more in diamond than it does in glass. Think you got it? Make sense? Just when you think you understand index of refraction perfectly, let's make it a little bit trickier. Every material has its own unique index of refraction. In fact, every material has its own unique indices of refraction, more than one index of refraction, depending upon what color is being used. Hold on before you write this down. I'll give you a chance a little bit later. Let me just explain it here first. When we shine white light, which is all the colors of the rainbow, right? Red, orange, yellow, green, blue, indigo, and violet, on a prism, say this prism is made out of glass, then that white light will bend because the index of refraction for glass is different than the index of refraction for air, right? Just like we had in our demonstration, when we went from glass to air and air to glass, light bent and we were able to see the boundary between the beaker and the air. Light bends when it goes into a new medium. How much does it bend? Well, it depends on what the index of refraction is. The bigger the index of refraction, the more light bends. But here's the thing. This prism has a different index of refraction for red light than it does for all the other colors. That means that red light, all the colors go in there, red light bends a certain amount, orange light bends a little bit more because there's a higher index of refraction for orange light. Violet light bends even more because there's an even higher index of refraction for violet light. Red light doesn't change speed as much as violet light. Okay? When you're going into this prism, the red light, the speed for red light decreases when it goes into the glass, and then it increases again when it goes out into the air. The speed for violet light decreases as well. Notice violet light's bending more, right? Violet light has a bigger decrease in speed when the light goes into the glass. But yet when it goes out the other side, it has a bigger increase in speed. The bigger the difference in index of refraction, the bigger the change in speed. And red light produces a lower index of refraction. Let's see. Red light would produce a lower index of refraction than would violet light. So red light changes speed more, violet light changes speed more, and therefore changes direction more because the glass has a higher index of refraction for violet light. That's called dispersion. When we separate all the colors of the rainbow from white light due to each color producing a different index of refraction in the material. Where have you seen this before? Some days when you're walking out of the school right past the cafeteria, sometimes you see a rainbow on the floor. You got to nail it within about a 5-minute interval. Okay, if you miss that 5-minute interval, then you're not going to see it. And you don't even see it all the time. Depends upon the season. Depends upon how high the sun is in the sky. Depends upon where the sun is in the sky. What happens is the light comes down through the windows at the top of the atrium, down through that corner display case, that triangular glass display case. White light goes through it and then splits up because red light bends less than violet light. In my house, my wife has this glass sphere with like edges on it. It's like a disco ball almost, except it's like glass, right? Like a decoration. And it's about this size, just a small thing about this size. And it's hanging in the window in our dining room. When the sun comes around, it's about 4 o'clock that this happens. When the sun comes around, it shines through this, and we get rainbows all over the wall. Like, it's actually pretty neat. Like, for about 10 minutes, you get these rainbows all over the place. And if there happens to be air coming up from the furnace vent, it causes this thing to spin a little bit, to rotate a little bit, and these rainbows are dancing all over the place on the walls from this little ball that's dispersing the light. Yeah, sure, I'll be right on that. Where else have you seen this dispersion taking place? Well, you got to get this one. Rainbows, right? That's a rainbow. Okay? Red light disperses the least. That's why at the top of a rainbow we see red light. But violet light will disperse the most. Therefore, we see Violet light at the bottom. It splits up because the Earth's atmosphere, the moisture in the Earth's atmosphere, creates a different index of refraction for each color. Doesn't happen so much when it's when it's not raining, right? Because you don't get those water droplets becoming the prism for you. Okay, give you a chance to write this down here now.